Welcome everyone to another installment of Desco's ESD training webinar series. My name is Greg Heckler and I'm the Western Regional Sales Manager. And today we're going to be discussing the basics of ESD control. We're also going to have a greater question and answer session today. So a lot of you, as you registered, you signed up and registered your questions, and our brand manager is going to be fielding those for us. So let's get started. Again, my name is Greg Heckler. I'm the Western Regional Sales Manager. And we also have Jim McKeon, who's our National Sales Manager. We're going to have Will de la Isla today, who's our Sales Manager for Mexico. We have Paul Rosas, and he's our technical support for all of our software-driven products. And then we have, as usual, we have Jeffrey Brake, who's the Desco Brand Manager. So let's get started. What is ESD? We're going to talk about that. We're also going to talk about the ESD models, which some of you may be familiar with that are in the ESD Association standard. We're going to talk about material types, and then again, we're going to have a lot of common questions today that everyone has. So what is ESD? Well, ESD is defined as an electric charge at rest. So basically we have static electricity there, but it's just sitting there. It's not ESD yet, which is what we're going to talk about. And static electricity is generated by what we call tribocharging, or when two surfaces contact and separate. So in this example of the roll of Scotch tape here, when I pull that piece of Scotch tape off the roll, I've now separated those two surfaces. And what happens when we separate those two surfaces, some of the atom electrons move and they cause an imbalance. And the imbalance is the static charge. So one of those surfaces will charge up positive and the opposite surface will charge up negative. And each one of those is a static charge. Again, in the example bottom right, when I walk across the carpet and I pick my shoe up off of that nylon carpet, I charge up positive typically, and the carpet or the flooring material stays behind negative. So each one of these is a charge, and each one of them can be damaging to electronic components. Other examples of ESD. Lightning is a perfect, very large example of ESD. Basically, on a stormy day, we have a cloud full of rainwater, and that rainwater, it's typically very cold up where that cloud is. We can have moisture or raindrops in there, and we can also have ice crystals in there. So what happens is that as those conductors contact and separate when the wind's blowing, we generate positive and negative charges. And when those charges get large enough, they neutralize each other, and that's what causes that lightning bolt. The lightning bolt comes down to Earth because the opposite polarity the polarity of the lightning bolt is looking for an opposite polarity, which is Earth, and that's what causes that lightning bolt. So that's a pretty common example. Hopefully you'll never have to experience a lightning bolt personally though. Now we're another perfect example of ESD or static generation. When I'm walking across the floor, if I'm not grounded, for instance, I am basically a capacitor or an isolated non-grounded conductor. So when I put that charge on my body, which is usually positive, and I go to reach for that negative doorknob or metal doorknob, I now discharge into that doorknob. And notice that I said when I reach for that metal doorknob, in order to have ESD, you have to have two conductive materials, and one of those has to have a charge on them. So in the case of the doorknob here, I have the charge on my conductive body, which is basically your sweat layer on your skin, and I go to touch that conductive doorknob, and that's how we have ESD in a nutshell. Oops, let me get here my next. So here's some examples of some of the charge amounts we might generate. Walking across the carpet, usually somewhere around 1,000 volts, depending upon where you're at in the United States or the world. It may be as high as 35,000 volts, sorry. Walking across vinyl tile floors, again, up to 10, 12,000 volts in many cases. And also keep in mind that the reason we bring up carpet and vinyl tile these are basically plastics. Carpet is basically nylon. We might open plastic bags, shop travelers, sheet protectors, things like that. So again, it's the opening or separating the two sides of the bag that generates the charge. Workers at a workbench. This is very common, certainly in the business that we're in. When somebody's sitting there soldering or working on their printed circuit board, they might be sliding around in their chair, getting up and down from their chair, etc., and moving plastics around on the workstation. So it wouldn't be uncommon to generate thousands of volts doing that. And again,
I can't help them. You guys can try and help them.
tape is a perfect Van de Graaff generator. We not only have the same piece of material or the same plastic, but we tend to tear that piece of tape off or pull it off the roll rapidly. So there's a few things that contribute to the amount of the charge. One is how fast I pull that off, what the material is. The more plastic it is, the greater the charge may be, and also the relative humidity. The lower the humidity, the bigger the charge will be. So that's why there's such a large discrepancy between these sizes of charges. A lot has to do with the amount of relative humidity in the environment. Okay, let's go to my next one. So this is an example of an actual ESD event. This company, High Rail Labs up in Spokane, Washington, they specialize in failure analysis. And this is a guy who hooked himself up to a magneto to induce a human body model discharge. And as you can see, that lightning bolt or discharge is coming off of his finger metal can. Now, in order to feel this charge, you had to have generated at least 2,000 volts, around 2,000 to 3,000 volts to feel that discharge. When you see this lightning bolt coming off your finger, that's about 7,500 volts minimum. So it takes quite a bit of voltage to see and feel. And that's one of the big problems in our business, is that if we're working with electronic components below this threshold or more sensitive to a couple thousand volts, we typically never see or feel the damage that we do. So I just mentioned the human body model. Excuse me.
What happened? No audio?
No, another screen popped up. I'm sorry. So I just mentioned the human body model. Now, in the early days of ESD control or static sensitive components, we basically had to wait until they failed and then test them and somehow assume or determine that it was a static discharge or static that caused the electrical overstress problem of the device. But now with scanning electron microscope.
Greg, hold on a second. Greg, hold on a second, please.
Okay.
I want to get the right PowerPoint up here.
Okay.
Okay, we're on the human body model, right?
Yes.
Okay. Can you see this slide, Paul? Okay, we should be good to go. Just ask me to move the slides now, Greg. Thanks.
Okay, I will. Well, do I need to minimize mine?
No, it's my screen now.
Okay, all right. Sorry about that. Okay, so again, back with the human body model. The human body is responsible or can be responsible for quite a bit of static damage. Obviously, we know we can generate a charge on our body, walk over and touch the leads of that component and induce that charge and damage the device. And so again, with scanning electron microscope and these models that the engineers have developed to simulate the human body, we can now test these devices, and the manufacturer of the component can now classify these devices as to their susceptibility and what their voltage threshold is. And so this is our most oldest common model. And this is all discussed in the ESD Association documents. But basically it represents a discharge into the device off of your fingertip. And again, this is the most common model that we have. We have another model, charge device model, or CDM. CDM is the opposite of the human body model. CDM happens or is when we charge up the component and then we ground it. And so that might be, oh, I slide a IC out of a tube and it touches a conductive surface, which I'll explain later, and it gets grounded and that causes the ESD event. Or maybe we have a charged device and we touch it with the tip of our soldering iron or a pair of tweezers. So one of our goals, as we're going to get into, is to keep from charging these devices up to avoid the CDM threat. Also, the industry is going to, or the ESD Association is doing away with that machine model. So mainly we're concerned about zapping the device ourselves or charging the component up and then grounding it. Here's some device sensitivity classifications, the ones that I mentioned. On the left, we have the human body model classifications, and on the right, we have the CDM classifications. As you'll see, class 0 are the most sensitive devices, up to 250 volts, and then all the way up to class 3, and we have subcategories as well. So if you were looking for the sensitivity of your device, you would consult your data book, and most of the device makers out there have an ESD section in their data books that tells you what this classification is or what the voltage threshold is. Now, the standard requires now that when you're writing your ESD plan, that you identify your most sensitive component. Obviously, when I protect down to my most sensitive device, all my ESD devices are safe then. So you want to identify that device. CDM is about twice as sensitive. So one of the reasons for that is your human body has a certain amount of capacitance, resistance to it. So when I zap a device, there's a little bit of let's say, a less powerful impact. When you zap a device via CDM, there is no capacitance or resistance in that discharge. So you have to remember that if I know my HBM classification, it may be twice as sensitive on the CDM side. So let's talk about material types that we have to deal with and that we have to control in our environment. One of the most important things we need to do is ground conductors. And there's leads of the IC, the human, whether it's the body, a conductive tote box, packaging materials, things like that, we need to keep those conductors grounded or at equal potential. Conductors, however, can be good and bad. Conductors are good when we do ground them because now they will safely dissipate that charge to ground if they get charged up or come in contact with a charge. If they're not grounded, they're capacitors basically, and they can hold a charge, which I'm going to show you in my demonstrations coming up. So we want to be sure that we keep all those conductors grounded. And in the case of the ESD Association standard S2020, it requires that all conductors be grounded. The other thing we have to deal with are what we call insulators, or in another word, charge generators. And insulators are the opposite of conductors. They don't have anything that makes them conductive at all. For instance, like carbon or metal or something like that. So that's why we're typically concerned about the plastics in our environment. So the reason why insulators are bad is because they can't be grounded. And so they will not allow electrons to flow across them. So in order to ground away a charge, the electrons have to flow across it and go to ground. So insulators are bad all the way around. And there's various ways of dealing with them that we're going to talk about. So again, it might be plastics, glass, dry air, things like that. Another terminology that we typically use in putting together a static control program that we need to be concerned with is the word dissipative. And basically, dissipative was coined with S2020 because what this means is something that will dissipate a charge away. And that could be a conductor, or it could be a static dissipative material like a piece of packaging material, a shielding bag, a low charging bag, anything that will allow electrons to flow across it and that you can ground or will dissipate the charges. However, there's a big range for dissipative, as you can see, from all the way from 10 to the 4th all the way up to less than 1 times 10 to the 11th. And this range is typically has to do with the application of the material. So for instance, an ESD work surface, we like that, or we need that material to be less than 1 times 10 to the 9th. That means if I set a charged IC on that ESD work surface, it will completely dissipate that charge away safely. Now, the standard also recommends that a work surface have a lower range of greater than 1 × 10⁶. So what that means is that I don't want to set a charge up device on a real conductive work surface, let's say like a stainless steel top in a clean room, because when I do that, basically I've set it on the doorknob and it will dissipate that charge too quickly and cause an ESD event. So we like to have a little buffer there as far as resistance goes for our work surfaces. As far as personnel goes, or grounding the human body, the standard requires that you be less than 35 megohms to ground. And they've determined that if I'm below that number, I can't have more than 100 volts on my body, which is the reason the standard was written, basically. Same thing with flooring. Now, the flooring standard allows you to go up to 10 to the 9th. However, you have to prove that you don't generate 100 volts or more. And we have ways to do that, test equipment to do that, that we can discuss later if you like. So let's get into the basics of ESD control. Oh, I haven't been, Jeffrey, I'm sorry, I haven't been telling you to change the slides, but we're. So
yeah, it's time to do the demo. We're going to do the demos now, Greg. So go ahead and turn your web camera on.
Okay.
Let's do those.
Okay.
Should be up. You're up.
Can you see me now?
Yep, you're good to go.
Okay, so what we're going to talk about today are some of the tools, first of all, that I have to do the demonstrations for you. And I have my ESD survey kit over here, which you can't see. Desco manufactures a survey kit full of all the tools that you need to perform an ESD survey or for compliance verification of your program. So I have a couple of those tools out of my survey kit that I'm going to show you. I have one of the tools that I have today is what's called a static field meter. Now, it's important to understand that if you want to measure static on something, you can't just take a voltmeter and touch your probes to your human body or to the IC or something and measure that charge. You need something that will measure the field that's sitting on top of that item that you're testing in particular. So that's what a static field meter does. I also have what's called a charge plate analyzer. Now, a charge plate analyzer, it still measures that same field, but it's more sophisticated in that it's obviously more accurate than the static field meter, but it also is a tool that's designed to measure ionizers or to test ionizer balance and discharge. So I'm going to be using this one quite a bit today too. They also make these, what we call these paddles here that come in the ESD survey kit. And we have one that's a solid piece of acrylic plastic. We also have another paddle that's a solid piece of aluminum on a piece of acrylic. So this one represents an insulator, and this one represents an isolated or a ungrounded conductor. And so via contact and separation, I can contact and separate these pieces of equipment, and I could show you how I can put a charge on that device. And so that's about 4,000 volts right there. It's also positive electricity. I'll also come over here and touch the charge plate analyzer. And you can see there's still about 3,000 volts on it, and you'll see the positive symbol next to that. So that means it's positive. I can then take this conductive one, and again, I can show you that I put a significant charge on here. I think you can see it's 3,000 volts. So let me touch here to make sure that you can see it. Again, 3,000 or 4,000 volts, except I now have a minus sign. And so, as I mentioned before, when you contact and separate two surfaces, one's always going to be positive and one's always going to be minus. Now, one of the nice things about these paddles is we can also show a couple of different things as to how we discharge static or how it reacts. I mentioned that you can't ground an insulator. So I have an ESD work surface here. So let's say this was my coffee cup or it was my water bottle or something like that. And some people might say, well, water bottle on the work surface. Well, I'm going to touch this to my work surface right now, touch it back to the plate, and you'll see that the charge is not dissipated. It's still there. You cannot ground an insulator because the electrons won't flow across it. However, let me show you this. So I'm going to charge this metal paddle back up. Now I'm going to touch the ESD mat. I need to ground my plate real quick. Now I'm going to touch the metal plate and bring it back in here. Charge is all gone. So these tools are great for training, for demonstrating the concept of ESD and static generation, but they can also be great tools to show whether the materials, say you purchase from us, mats, flooring, etc., that they're actually working and dissipating a charge. So that's one other thing. So what's next, Jeffrey? What should I show? Come back in, Jeffrey. Hang on a second, please. Okay,
I'm here,
so,
Greg. Sorry,
okay.
can you show, did you ground the metal one?
Yes, I did.
Okay.
So again,
So let's go ahead and,
now the charge is gone. Okay, what's next?
let's go ahead and get into some of the questions that were provided.
Okay.
Let me bring up my screen here so I can see what I'm doing. I don't know how to do that. Okay, so the first question we have was provided to us through registration was when designing and developing a work area for an ESD workstation, what are the building blocks and processes? This is kind of a long question. To answer that question, I have Jim McKeon. Let me see if I can get Jim on the line here. Jim, are you there?
I'm there, Jeffrey.
All right, Jim, you see the question?
I do.
Okay, go ahead.
I'm in a room. Let me ask you a question. I'm in a room with an echo. Is that okay?
You sound good.
Okay. So the first thing that you need to do is identify an ESD protected area, which is an area where all of the rules that you decide to implement for your ESD program need to be in place. But in terms of designing a specific workstation, as Jeffrey said, this is a potential long answer. But the next 4 bullet points discuss the 4 basic guidelines of an effective static control program. Number 1 is that you need to ground all personnel who handle unpackaged static sensitive devices. So if we're talking about a seated operator at a workstation, then you're talking about a wrist strap. The second guideline is unpackaged static sensitive devices need to sit on a properly grounded ESD surface with resistance of 1 × 10⁶ to less than 1 × 10⁹. So you're talking about some kind of an ESD work surface. It could be the bench system could have an ESD laminate. It could be a mat of some sort, but we want to ground the person and ground the product. And if neither of those have a charge on them, then there can't be any discharge, the D in ESD. A third building block is that if you have to have an insulator on the work surface, generally we like to say it should be 12 inches away from any unpackaged static sensitive devices. There are more details than that, but you know, as Greg mentioned, coffee cups, things like that, and any items that have to be in the area should either be 12 inches away from devices, or you should use ionization. And then you have to decide how items will be packaged and transported. How are they coming into this station, and how are they leaving the station? So just quickly to go back to review the answers to that question. If you want to have a basic ESD workstation, you need a wrist strap, you need a mat, you can't have insulators prominently on the workstation, and you need to use the right kind of packaging to bring devices in and have them leave. A little bit beyond that is a compliance verification plan. So in S20.20, it stated that all the elements of an ESD program need to be tested. So that all those items, wrist strap, mat, insulators, they all need to be tested, some at various time frames than others, but that's also part of it. So that's very quick and very basic, but
Great. Greg, can you demonstrate how packaging, ESD shielding packaging works?
Yes. So here I have a static shielding bag. Now, and that's something that important to understand. Here I basically have a low charging, or a lot of people might call it an anti-static bag. And the main difference between the two is this won't generate a charge, but it will also allow a charge to go through it. So originally, when the static shielding bag was invented, basically you have to have what's called a static shield or a Faraday cage. And in order to have a Faraday cage, you have to have metal. So inside a static shielding bag is aluminum, except that the aluminum is so thin that I can see through it. So one of the things I can show you is I can charge up my plastic paddle again. I will show you.
Can you look this up so I can see? I can't.
The bolts.
I can't see the webcams.
Plastic paddle. I can put it inside my shielding bag.
Don't worry about it. No. Yeah.
I can touch my shielding bag to this. Oh, let me zero this out. Touch my shielding bag to this, and you'll see that there's no charge. So static shielding bags not only keep charges from going in, but if you have something that has a charge on it, inside it won't come out either. So either way, the charge isn't coming in or the charge isn't going out. So the importance of static shielding bags is that if my device isn't on a grounded workstation or an ESD controlled area, that I need to keep my components, circuit boards, etc., in a closed shielded container when I'm transporting those devices. Hey, Jeffrey.
Thanks, Greg, and thanks, Jim, for that answer on that question. I appreciate it. Next question for me, why should wrist straps be worn when seated at a workbench? There's kind of, we're going to go forward. There we go. There's really two reasons. The first is that's what the ESD Association's S2020 document, which is the document we use to, which is used by the industry for standards for ESD control in an electronics workplace, says that a seated operator must wear a wrist strap. So that's the first reason for doing that. The second, more practical reason for doing it is that in the diagram there, you can see if you're wearing foot grounders and that's your primary method of grounding, if you pick your feet up, you're not going to have a good connection to ground anymore. So that's why it's the S2020 and the ESD Association recommends that. And for practical reasons, that's why you do it. Greg, do you have a chair that you can do a demonstration of that and show a charge generation?
Yeah, so I'm going to slide my typical, office seat over here, chair over here, and I'm going to sit it down in it. And I've got my feet up on the chair ring right now. And so I'm going to touch the plate and you can see the amount of charge that I have on me. So now I'm going to put my foot grounder on my conductive floor and you'll see that the charge is off, okay? So once I pick my foot back up, the charge comes right back again. So again, not only would I not be grounded per the standard, but I'm going to generate a charge if I'm not seated. So I'm going to stand up and look at the difference in the charge when I come out of that, nylon material and the thousands of volts. Okay. I'm going to sit back down, put my foot grounder back down, and now I'm grounded. So the odds of you having your employees having their feet on the ground all the time, they're not very good. So wear your wrist strap. Okay, Jeffrey?
Great. Thank you, Greg. Next question. We get this a lot. Is pink polyfoam ESD safe? I'm going to bring back Jim McKeon to answer that one. Jim?
Thanks, Jeffrey. Can you go to the next slide? Thanks. So one of the things that we see a lot is the use of pink foam as a cushion for static sensitive devices, whether it's on a work surface or part of a tray liner, as a tray liner on a cart or on a shelf. So the main purpose of pink poly is to be a material that doesn't generate a charge. It's not designed to be used as part of a ground path. such as on work surface, car trays, and shelving. And the reason for that is even the best pink poly, even brand new pink poly, if it doesn't generate a charge, it still is going to have a resistance of greater than 1 × 10⁹. So you can have the best setup work surface, the best setup cart, the best setup shelving. If you introduce a piece of pink poly foam or any material that's greater than 1 × 10⁹, then you have just made that whole system out of spec. The other problem with pink poly is that it's not permanent. So the way that it's made is there's an additive put into it when the material is extruded. That additive blooms to the surface and collects moisture from the air. Over time, that additive will bloom to the surface and you'll be left with just a regular piece of plastic. So it's important that if you're using it for packaging and you're not, don't have any static shielding bags around the devices, that you know how much charge it generates by using a field meter and seeing how much charge it generates. And at 1 inch, it's got to be less than 125. And at 2000 volts, it's got to be greater than 12 inches.
Great, thanks, Jim. Greg, do you have pink poly there at all? Any foam?
I don't have a piece of pink foam. You know, I might hang on.
But could you? How about?
I do actually.
Could you show?
What would you like me to show?
Try to show the resistance to ground of pink poly through the workstation, like Jim's talking about there, in the first, and see what we get.
Okay. So I'm going to set my. Oops. I'm going to set my. Goes my field meter. I'm going to set my pink poly foam on the workstation. I have my surface resistance tester that's in my survey kit. I have my 5-pound weight, and if you were here last week at our presentation, you'd see we did all the resistance measurement tests. But basically, what I'm going to do is an RTG test, or resistance to ground. So my black lead is attached to my AC ground point, and then I have my test probe here, and I'm going to run my test. And this test takes about 15 seconds to make. So I have 3.54 times 10⁹. So out of spec. Remember, a workstation has to be less than 1 × 10⁹ to be in spec.
Perfect. Thanks, Greg, for that demonstration. Thanks, Jim, for the answer. Please stay around. I think there's some more questions for you.
Okay.
Next question. This one's for me. What's the best way to clean ESD footwear? For daily cleaning and sort of periodic cleaning, you can use a tacky mat. You can put these at the in front of your testers or entryways into the work area. So that'll remove most of the dirt and grime that builds up on foot grounders. Foot grounders are pretty durable products, at least the ones we make are. So they're meant to be walked on. They're meant to get a little dirty. Most of the time, they'll still function just fine for testing and for use in the EPA. If they get extremely dirty, or if you feel like you need to clean them a little bit more, use something like an ESD cleaner, like the ESD Restore cleaner that Desco provides. You can take the foot grounders off, scrub them down, clean them up real good. ESD Restore doesn't have any insulative residues that'll leave behind. So a cleaner like that's going to be better than some normal household cleaners. So that's the best way to clean them. If you feel like your foot grounders are getting dirty, or that's what's causing you to fail at your daily testing. Next question is going to be for Will De La Isla. Will, are you there?
Yeah. Hello. Can you hear me?
So, yeah, we can hear you. Thanks. For Will, the question is, what is the purpose of an ionizer?
Well, air ionization is going to be your last line of defense. So Go ahead and hit the next slide. Air ionization neutralizes static charge on an insulated or isolated objects by producing a balanced source of positive and negative charge ions. Whatever static charge is present in an object in the work environment, we will reduce and neutralize by attracting opposite polarity charges for the air. What does that mean? We're basically fighting fire with fire. So if there's a static voltage in the work environment, our air ionizers produce the opposite, and in a neutral state, if 7,000 kV a positive, 7,000 kV a negative, and it's gonna remove the charge. So I think Greg Heckler has a setup here with an isolated circuit that he could demonstrate how a charge can be produced on an isolated circuit and how the ionization will remove that static charge from creating an ESD event. So Greg, can you illustrate that for us?
Yes, thanks, Will. So inside the survey kit, there's what's called a ionization test kit. And basically it takes the static field meter and it has this hood, which is isolated from the case of the field meter by these standoffs. So now I have an isolated conductor by which I can collect the ions that I'm going to put on the conductor. And that's with this little static generator or voltage generator that we have. So this is one test method or piece of test equipment I can use. You can also use a charge by analyzer, which I described. So I'm going to put a charge on here. And as you can see, I'm putting on about 1200 volts or so. And now I'm going to come over, I'm going to hold this inside my ionizer real quick. And as you can see, it dissipated that charge. So the important thing to understand about ionizers versus other methods of static control, say like raising the humidity in the environment, is ionizers neutralize that charge very fast. Another thing that they do that a lot of people don't think about is that when they're running continuously on your workstation, it's also very hard to generate a charge on something. So they keep things from charging up, and if something has a charge on it, they properly neutralize that charge. The other thing you can do is more of a practical real world thing. You can use your paddles again. Again, I can generate a charge on my I'm holding it up so it doesn't get in the ionization. I can generate a charge on my plastic paddle. Now I can see if this was some piece of plastic I'm working on, I can see now that it's completely discharged that charge from my plastic paddle. So those are a couple little tools that we would use, a couple of tricks that you can use just to make sure that your ionizers are neutralizing the things that you bought them for or purchased them for. Okay, Will.
Thanks, Will. Thanks, Greg, for the demonstration. Next question, Jim Kean again. Why do I need an ESD Smock? Jim?
Yes. Can you go to the next slide, Jeffrey? So the purpose of a smock is to attenuate electrostatic fields charges that might be present on a person's clothing. To go back to Greg's previous slide and explanation of charge device model. So a person's clothing can be charged, particularly in the winter months when it's drier and of course dependent on the material. So if the person is leaning in or very close to the static sensor devices at a workstation or a slide line, that charge from their clothing can be induced onto that device, and then depending on how that device is handled, there's a possibility of a charge device model event happening. So the purpose of the smock is to prevent the charge from the clothing from going onto the device. I like to describe it as a static shielding bag for clothing. So nothing, the charge from clothing won't go onto the device, and generally a smock will allow you to meet all of the requirements, the 125 to 1,999 volts at an inch and 2,000 volts at 1 inch.
Great. Greg, can you demonstrate that? I think you have a tray there that you can show us how that might work.
I do. So as Jim mentioned, the static shielding bag concept, and as I demonstrated, not only will shielding bags keep charges from getting in, but they'll keep charges from getting out. So that's what we're concerned about with with our garments, our clothing. So this is a very common tray that's got to load it up with circuit boards, or it might be an open tote box, or anything where the product isn't already shielded. If I were to pick this up and walk across the room, which somebody is very common holding a tote box, and I wasn't wearing my smock, I might induce the charges onto my circuit board. Consequently, if I was sitting at my workstation like I was before in my chair, and I slide into my workstation and I start soldering, or I'm looking under my microscope, I can also induce those charges from my clothing. So a good conductive smock or garment, a very low dissipative garment, say in the 10 to the 6 range, is very good for attenuating a charge and keeping those charges from getting out. When you wear a smock like this with a conductive cuff, I'm also grounding the smock as it's touching my body, and I'm wearing my wrist straps or foot grounders. So now I have all conductors grounded, and I have something controlling the charges on my clothing from getting out. Okay, Jeffrey?
Greg, thank you for the demonstration. Jim, thanks for the answer. Next question here is, for workstation mats, what are the required tests for compliance verification? Well, in the S2020 document, there's a couple tables. Table 3 has most of the elements for an ESD control plan. One of those is work surfaces, which also includes trays or carts or anything that you're using to put an exposed ESD susceptible device onto. So the limit there is less than 10 to the 9th. So it's an RTG test. So the picture there depicts how you would do it. One lead on the table and the other going to ground. You also typically you want to test the area that's most used at the workstation. But if you have some outlying areas, so if you have a 2x3 mat, you might want to check a few areas. But for sure, check the most used area. Greg, do you have an arm meter that you can do a compliance verification test on a workstation mat for us?
Yes, thank you. So I'm going to bring my surface resistance tester back in again with my 5-pound probe. Now remember that the standard for compliance verification only requires, or it's only mandatory to check resistance to ground. We know we have 2 5-pound weights, so we don't use those unless we have a failure. So I'm just going to check the resistance to ground again. I'm going to set it on the front edge here that you can see, and I'm going to run my test. And the requirement is less than 1 times 10 to the 9th. So also over 10 to the 6th, it's required that you energize for 15 seconds. So this tester is automatically doing that for you. So 1.4 times 10 to the 6th. So it's well within that range required to properly dissipative charge. So we know that the more conductive something gets, the faster it's going to dissipate that charge. But again, we want to control that in the dissipative range. So greater than 10 to the 6th, less than 1 times 10 to the 9th. Okay, Jeffrey?
Great, thank you, Greg. I just want to reiterate that when Greg does that test, or when you do a compliance verification test like that, you're testing the surface of the mat, and then whatever path to ground that it's using. If it's grounding through the laminate or it's grounding through the ground cord, you're verifying that you have a path back to the electrical ground.
Right.
Thanks again, Greg.
Jeffrey, let me add. So here's another, this just happens to be green. Here's the same 2-layer rubber mat material. You'll notice the color side, that's the dissipative side. And on the bottom, that's the conductive side. So this is the ground plane that Jeffrey's talking about. When the charge goes on the surface, it goes through the surface, and then it speeds off to ground. So the intimate surface is what we want to be dissipated.
Great, thanks, Greg. Next question, again for Jim McKeon. What's the difference between grounding with a wrist strap opposed to an ESD Smock? Jim?
Thank you, Jeffrey. Well, the requirement for resistance of the person, the wrist strap, and the cord is less than 3.5 times 10 to the 7th. And generally speaking, in most cases, operators have put the wrist strap band on, attach the cord to it, go up to the tester and test. If you're using your smock, as part of the grounding system, which a few weeks ago we talked about Smocks, and we talked about a groundable static control system. The resistance of the Smock connection to the wrist, the connection from the band, the knit cuff to the snap on the Smock where the band, the cord is connected to, and the person also has to be less than 3.5 times 10 to the 7th. So the difference in required results is no different. The difference is that when you are using your Smock as part of your grounding, your wrist strap grounding system, you need to test the wrist strap the way that you're going to be using it. So you need to wear the Smock and test while you're wearing the Smock and have the system set up the way you'll be using it during the day. But the required results are the same for both, less than 3.5 times 10 to the 7th.
Great, thanks, Jim. Next question here. How often should foot grounders and wrist straps be tested? I'm gonna go to Paul Rosas, who's our technical support manager. Get him on here. Self-muted, Paul.
Okay, you guys hear me?
Yep.
Thanks, Jeffrey. If you flip to the section in the S2020 under 7.4 compliance verification, you'll see that the recommendation is to perform testing daily. Now, you're not limited to doing this daily. In our experience, doing it anytime the operator leaves and re-enters the EPA is suggested. Circling back to Jeffrey's previous topic of cleanliness of foot grounders, depending on the environment, they typically will get dirty. So it's best practice to test each and every time the operator leaves and re-enters the area. And also under compliance verification, you'll see that these records of your daily testing need to be recorded. So Desco offers a wide variety of testers that allow you to accomplish this. We have the X3 Desco combo tester, which paired with a paper log would allow you to capture this in that form. But our recommendation would be to capture this digitally with what we have as our Smart Log Pro. As you grow, your logs will grow. So the best way to record this information and track it is digitally using a Smart Log Pro system like Desco Emit offers.
Great, thanks, Paul. Appreciate that. Next question here. Why shouldn't ESD personnel grounding, wrist straps, foot grounders, or smocks be used when working around high voltage, 250 volts or more? This is spelled out in the ESD Association's S2020 document in a couple ways. First and foremost, it states that safety takes precedent to your ESD control plan. So if you have a situation where there's a conflict between ESD control and safety is going to override that. So the first thing you want to establish is your safety control program or your safety program, and then your ESD control program. Secondarily, most wrist straps don't have a resistor in it that's rated for 250 volts, and Desco wouldn't make them either because there's additional safety issues with that also. So the basic reasons for not using wrist straps or grounding mechanisms for people is a safety reason. You can use ionization, and there are some other precautions you can take for ESD control at high voltage areas, but grounding people is usually not recommended. I do want to point out one thing, Greg. I think there's a monitor there at the workstation you're at.
Yeah, it's back here.
Can you show us how the monitor will verify that a normal ESD control wrist strap has a resistor in it?
Yes. So the continuous monitor that I have back here right now is monitoring the connection points to my work surface. And I'm also have my wrist strap and cord plugged into it. So right now it's monitoring my body's upper resistance limit, and it's making sure that I'm less than the 35 megohm that the standard requires. So right now I've got all green lights. So real quick, as far as the monitor operation, if I were to have a break in that connection, I'm going to get an audible. So now I have a high resist situation. So that tells me that I'm above that resistance. However, in your tester, your touch tester also, you have a setting in there that makes sure you're below, or you don't go below 750,000 ohms also. So our tester has a delay in it. When I remove my wrist strap, it allows me to park my cord on it so I don't get false alarms. This particular cord that I just plugged into it, you'll see it's got a red head on it. The standard requires that if there's no resistance in your cord for some reason, let's say you're handling explosives or something like that, that you don't use a resistor in there. So this cord doesn't have a resistor, and you'll see when I touch it, I'm grounded now. My monitor is still alarming because it's sensing the presence of no resistor in that. So the great thing about this type of monitor, it will alert you to a safety issue also. So again, I plug my regular wrist strap back in, and now I've got above my 750,000 or 1 megohm of safety resistance in there, and everything's good. Okay, Jeffrey?
Perfect. Thanks, Greg. So that concludes our presentation today. I want to thank everybody for the questions they provided when they registered for the webinar today. We're probably going to do this a couple more times where we take your questions and answer those in sort of a long format like we did today. So we appreciate that. Of course, we're always available. If you have a question that you need answered right away, feel free to contact us. Greg's contact information is up there now, but anybody at Desco can help you find the answer you're looking for, or find a person who has the answer that you're looking for. So thanks again, Greg. I want to thank you. I want to thank all the guys who participated and helped answer these questions today. Thanks again.
Thanks a lot, everybody.
Thank you for joining us. Another reminder, all these webinars are archived on the Desco homepage at desco.com. So if you missed one of the webinars over the last few weeks, feel free to go back to it. Or if you want to share this with somebody else, please do that. We appreciate it. Thanks.